Okay, last time we talked about arithmetic sequences in series where we were adding up sequences where we were adding or subtracting the same amount each time. We called it a common difference. So now we're moving into geometric sequences where a geometric sequence is defined if consecutive terms have a non-zero common ratio r. So if we're going to define these recursively, we would say the first term is whatever the first term is, and then we would say the next term is found by taking the previous term multiplied by whatever that common ratio is. The generic explicit form is that the nth term of a geometric sequence is given by the first term times the ratio to the power of n minus 1. So don't forget in your mind to keep track of how this is similar to our arithmetic case where a sub n was equal to the first term plus n minus 1 times the common difference. The difference here is that instead of adding, we're multiplying, and thus instead of multiplying, we're exponentiating because of multiple copies of the ratio. Okay, so the first example asks us to show that each of the following sequences are geometric. Find the common ratio, write out the first four terms. Okay. So when they're written in this nice exponential form, it's very clear what the common ratio is. The common ratio here is negative 3. Negative 3 because that's what's being raised to the nth power, right? And that's what the ratio is going to be raised to some kind of power. There's a little bit of correction going on, but it gives us what the ratio is. Similarly, over here, since we have a power raised to the 2 and a power raised to the 3 to the n minus 1, right, so it's still got a power on it, the ratio over here is pretty clearly going to be 2/3. But now to be more formal with it, let's write out the first four terms and then do what the question's asking for. So the first term would be replace n with 1. Negative 3 to the 1 is negative 3. To the 2, 9. Negative 3 cubed is negative 27. And negative 3 to the fourth is positive 81. So we can see that the common ratio is indeed 9 divided by negative 3, which is negative 3, or negative 27 divided by 9, which is negative 3, etc. And then over here, we can see that if we were to replace n with 1, we would get, let's see, 2 to the 1, which is 2, over 3 to the 0, which is 1, so we get a 2. Replace n with 2, then we get 4 over 3. Replace n with 3, we'd get 8 over 9. And you can already see that the ratio is becoming a 2/3 multiplier, right? 2/3, 2/3. So the next one's going to be 16 over 27. So that shows that it finds the common ratio and also has us write out the first four terms of these particular sequences. Okay, next page asks us to find an explicit algebraic formula for the nth term of the following geometric sequence. First one's awesome, right? First term is 3, common ratio is negative 2, so that means that a sub n would be equal to the first term times the common ratio to the power of n minus 1. That completes that problem, no big deal. Over here, they were giving us only the third term, so they didn't give us the first term. They tell us that a sub 3 is equal to 7, but I know how, if I'm going to multiply by a ratio of 1/3, that means that going backwards would be multiplying by the reciprocal, which is 3. So a sub 2 must be 21, and a sub 1 must be 63. So here I would say that the nth term would be given by 63 times the common ratio to the power of n minus 1. What if we need to move on to these ones? Now these ones, they didn't give us any initial conditions, we just have to look at it and see. So here a sub n equals, the first term is clearly 5. The common ratio is given by looking at what happens to get from 10 from 5. 10 divided by 5 is 2. 20 divided by 10 is 2. 40 divided by 20 is 2. So my common ratio is 2, and that's raised to the power of n minus 1. And finally, over here, I actually have an easier time if I think of these in fraction form as 1/10, 100th, 1,000th, etc. Because then I can clearly see that my first term is 1/10, and my ratio is to multiply by 1/10, and that's to the power of n minus 1. So in this case, I might actually write it more simply as 1/10 to the power of n. But that's how we would solve the problems on this page. Okay, moving on. If we need to find the sum of the first n terms of a geometric series, so technically a geometric series is infinite, but if we're really talking about the finite sum here, or what we might call a partial sum once you get into more advanced math classes, is when we're working with these problems, we want to add up the first n terms of some geometric sequence. We know what the pattern is, and we can prove this formula by induction, but for here we'll just accept it on faith, that when you add up the first n terms of a geometric sequence, you end up getting a1, 1 minus r to the n, over 1 minus r. So that means if we wanted to apply that to particular problems like down here, it says find the sum of each of the following. So here we can see that the first term, so we want to add up the first, how many terms? 1, 2, 3, up to 15. So we want to add up the first 15 terms of the sequence, which would be a sub 1, the first term, 3/9, times 1 minus the common ratio. So I can see that I'm only multiplying the numerator, right? The denominator stays the same, so my common ratio is 3 raised to the power of n, which in this case is 15, and that's over the quantity 1 minus 3. So let's break out a calculator and see what we get. We get 3/9, also known as 1/3, multiplied by 1 minus 3 to the power of 15. Whoops, forgot to multiply, so let's just bring that in. Ooh! Divided by 1 minus 3, that's -2. So it looks like our answer is 2391484 and a third. Now we're not surprised that these get large, right? Because these are exponential, right? They're multiplying, so they're going to get very, very large in the long run. But that gives us kind of an idea of what's going on. Let's try B. So in B it says we're adding up 5 times 3 to the k minus 1 from 1 to 12. So again, we want to add up how many terms? 12. The first term is what we would get when we plugged in 1. 1 minus 1 is 0. 3 to the 0 is 1. So we get 5 times 1 minus, the multiplier is 3, and we want to go to the 12th term, so that'll be over 12, and 1 minus 3. So according to our calculator, we would get 5 times 1 minus 3 to the 12th all over the quantity 1 minus 3. That seems to be 1328600. And if you want to get really excited, check this out, math. Let's do a summation on this one because it's written in an appropriate form for us. K equals 1, I'll do x equals 1 to 12 of 5 times 3 to the x minus 1. Hopefully it's the same. Yeah! So we can see that it's getting exactly the same answer. Very happy. Down here then, let's do this one quickly since we have our calculator active anyway. Let's just turn that one on and say, what is the sum from x equals 1 to 10 of, whoops, I think I got into a bad place here. Let's go out here, go in there, alpha f1 1 over 2 to the x. Nice. 1023 over 1024. 1023 over 1024. And then finally, on this one, They ask us to do it, but notice how they're messing with the bounds on the summation starting from 0. But since we are at least to get the answers to this using the calculator, let's just do x equals 0 to 6 of 2/3 to the k. 2/3 to the x in this case. Answer is, can I change it into a fraction? Yes, there we go. 2059 over 729. Okay, make sure to try these out with the formula and also with the calculator so we know how to use both. Okay, so a geometric series now is technically an infinite series, and what's nice about multipliers with geometric is that when you're multiplying by a number that's less than 1, your terms are going to shrink, right? If you keep on thinking about it as half of half of half of half, it keeps shrinking and getting smaller. So numbers that are less than 1 will work well. So when we have a geometric sequence with the first term and a common ratio, the sum of the first n terms is given by this formula, as already discussed. We would say that the infinite series that adds up infinitely many terms converges if we approach a real number, and that it diverges if we fly off to infinity or if we oscillate between plus and minus infinity. So the interesting thing is that as a conclusion is that if you have a sequence, a geometric sequence in which your magnitude or the size of your ratio is less than 1, then you'll converge to become a1 over 1 minus r. And if the size is bigger than or equal to 1, that just means you keep growing and growing and growing, or you keep on adding more and more and more. That just simply means you're going to diverge. So that leads us to these problems now. Determine if the sum converges or diverges. So determine if the sum converges or diverges. So here your common ratio is 4/3 divided by 2, which is 2/3. So this will be converging. What does it converge to? Well, it converges to the sum of the first infinitely many terms is going to be the first term, 2, over 1 minus the common ratio, 2 over 1/3, which is 6. Done. Over here, if we want to figure out what our common ratio is, right? That was the ratio. The ratio is the second term divided by the first term, which is 4/3. Unfortunately, that's bigger than 1. That means this one automatically diverges, and we don't have to do any more work. When we come down to this one, infinite sum again, the common ratio is 1/3, so we already know it converges because r equals 1/3. So the s infinity is going to be the first term. What do we get when we plug in 1? 8 over 1 minus that common ratio of 1/3. So 8 over 2/3, that's 24 over 2. That looks to be 12. And finally, over here, the ratio in magnitude is also less than 1, so this is going to be converge. And our sum is going to be a sub 1. S infinity is going to be a sub 1, the first term. When we plug in 0 in this case, negative 1/2 to the 0 is 1. 4 over 1 minus that common ratio of negative 1/2. So we get 4 over 3/2, which would be equal to 8/3. And that completes these kind of problems. Okay, now here's kind of a surprising result. A lot of students are surprised by this, that 0.9 repeating is actually literally equal to 1. And we can see this very clearly if we think of it as an infinite geometric series. 0.9 is 9/10, 0.09 is 9/100, 0.009 is 9/1000. And so if we were to add this up infinitely far, what would we get? Well, this is an infinite geometric series. Agree? What is our common ratio? Well, each time we're multiplying by 1/10. What is our first term? The first term is 9/10 divided by 1 minus that common ratio, which is 1/10. So we get 9/10 over 9/10, and anything divided by itself is clearly equal to 1. And so we're seeing here that 0.9999999 is exactly equal to 1. Okay, last part of today is applications, which are word problems, right? So in our word problems, let's first say that Jim Bob is investing some money in a mutual fund. The annual rate of return is 8% compounded monthly. How much will Jim Bob have after 360 deposits? So let's assume that the interest is calculated at the end of the month. So the first deposit or the last deposit he puts in at the end of the very last of the 360 deposits would be worth $400. He doesn't get any interest on that. The money that he put in the month before the end would be 400 times 1 plus the interest rate divided by that monthly division to the power of 1. 2 months before the end, he would have 400, 1 plus 0.08 divided by 12 to the power of 2 because it got 2 months worth of interest. Plus dot 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 dot. And the one that he puts in at the end of the beginning would be worth what? 400, 1 plus 0.08 over 12 to the power of 359. Because remember, he's putting it in at the end of this month, 359, because it doesn't get that extra little bit of interest. So how much will all this money be worth after these 360 deposits? What's the sum of the first 360 deposits? That would be first term 400 over 1 minus the common ratio. And the common ratio that we're multiplying by each time is 1 plus 0.08 over 12. Right? That's a sub 1 over 1 minus the common ratio. And this is, oh, whoops! That would be if it was infinitely long. We're not doing infinitely long, we're doing 360. So it's first term 1 minus the common ratio, 1 plus 0.08 divided by 12 to the power of how many deposits are there? 360. All over 1 minus 1 plus 0.08 over 12. Okay, I'm sorry for smashing that in there. That means I'm going to have to put this answer in the calculator. I just don't have a, well, I can't do that in my head anyway. But let's see. 400 multiplied by 1 minus 1 plus 0.08 divided by 12 to the power of 360. Close the numerator, divided by 1 minus 1 plus 0.08 divided by 12, close the denominator. There is our answer, 596143.78. So it looks like almost $600,000. Think about that in context, by the way. If we think about $400 per month, multiplied by 12 months in a year times 30 years, you've only put $144,000 in the bank out of your pocket, but it's worth $600,000. That's why it's really important to save early and often. Okay, our last problem is somebody named Samwise is dropping a ball from a height of 2 meters. Each time it drops, it goes to 75% of its previous height. So, what's going on here? This is going to be infinite, right? The ball keeps bouncing and bouncing and bouncing. So it drops 2 meters, bounces up to 0.75 times 2, which would be 1.5, comes down 1.5, bounces up, bounces down, bounces up, bounces down. And so we have the downward motion and the upward motion that will add up separately. The upward motion is first term. This is infinite, right? It's going to keep on bouncing and bouncing and bouncing. So we got the first term over 1 minus the common ratio. 75% is 3/4 as a fraction. 2 over a quarter, and that's equal to 8. The downward motion is the first, upward motion. This is actually the downward motion because the first downward motion is the 2. The upward motion, when we're moving upward, the first upward motion is actually 1.5 over 1 minus 3/4, which would be 1.5 over 1/4 times 4, which is 6. And so altogether, when I bring together the downward motion and the upward motion, together that gives me 14 meters of total motion.